All right, so this is part two, the more complicated part of doing some radiometric dating math using the uranium to lead decay series. The last video we went over how to find the age of a sample if the parent to total isotope count landed right on one of these fractions. It'd be pretty easy, right? So this video we're going to go over an example that doesn't fall directly on one of those fractions. So, so we're going to pretend that we work in a lab that does these things, and we pulverized our zircon crystal, and we've run it through the counter, the detector, and it's counted up for us. And I happen to have a student in class, just one, but hopefully that will help slow me down, and hopefully that student can ask some questions and whatnot. But I'm going to have her go ahead and give me some numbers. So give me a number just so we can make up a fraction. Okay. So give me a number between 1 and 20.
7.
7, she says. 7. All right. So we're going to say that we got a fraction. I'll leave this here. Let's say we got a fraction of 7 over, and now give me a number between 7 and 30.
13.
13. All right. So what that means here, if this is the number numbers we're working with, what that means is we must have gotten a count back from our detector for detecting isotopes. And then we probably reduced that fraction down as far as we could, and we came down to 7/13, which means that we have 7 parent isotopes for compared to or in relation to a total of 13 parent plus daughter isotopes. Okay? So in this decay series, those parent isotopes are uranium and the daughter isotopes are lead. Okay? So where do we go from here? Well, we want to know how old our sample is with this fraction. Where does that fraction fit in our chart? So, student, how does 7/13 compare to a whole? Does it go in between a whole and a half? Is 7/13 more or less than a half? She's using a calculator.
More.
Is more than a half?
Yeah.
Okay, so it's more, because half of 13 would be 6.5, right?
Yeah.
Okay, so we're just a little over a half. So if we're more than a half, that means this fraction fits right here in between a whole and a half. All right, so we already know that our sample, based on the fraction of parent to total isotopes in our decay series in our sample, we already know that our sample is somewhere between 0 and 710 million years old. So it's not all that old when you're talking about zircon crystals. It's a pretty fresh one, okay? So now what? Well, what we do is we take this column and we turn it horizontally, and we basically turn it into a timeline, okay? But then we also keep our fractions here on the ends of that timeline as well. So let's turn it and open it up. So on this side, we're going to have 0 years, right? Brand new. And then way over here on this side, make sure that we can see that in the video. Good. All right, over here, we would have 710 million years. MY for million years. Okay? So that's the timeline aspect of it. And we got to figure out, where does our sample fall along that timeline? How old is it? All right. But then on the bottom, down here, we're going to put the fraction that goes along with that age, right? So obviously 0 years, we'd have 1 over 1. And at 710 million years, we'd have a half of that parent material left, because it's 1/2 left. So we'd have half the parent isotopes left in the sample. We have a little more than half, so we're going to be in between. So the next step, if we're trying to use a number line and we've got fractions, we need to have a common denominator in all three of those fractions. Otherwise, we won't know where it goes. Okay, we won't know where our sample goes on that number line. So we have to be using the same denominator. So we've got to come up with a common denominator. This is going back, what, a year or two? Two years? When you all learned how, 2 or 3, when you all learned how to find a common denominator. So we have 1, 2, and 13. What is the least common denominator? In other words, what can 1 be divided into, 2 be divided into, and 13 be divided into? I'm pausing. The mind of the student is running. 26, yeah. Because you can divide 26 by 2. You can, of course, divide 26 by 1. And you can divide 26 by 13. Okay? So 26 is our least common denominator. So what I'm going to do here is I'm going to change this whole. It's still going to be a whole, but we're going to use 26. Okay? So it'd be 26 26ths. That's still a whole. Okay? And a half of 26 is 13. So this is going to be 13 26ths, which is still a half. But we're using a common frame of reference. That way we can place that sample on the number line. And then our sample itself would become what? If we're doubling the denominator, we also have to double the top, right? The numerator. So if this becomes 26, that becomes 14. So we'd have 14 26ths. Okay? So that's what this becomes. So I can put a line through here and say, you know what? We're not using that fraction anymore. We're using the 14 26ths. Now you can count from 13 to 26 evenly. There'll be even increments of time when you do that division. Okay, so what's the division? Well, how many increments would you have? How many numbers would you have between 13 and 26? 13, right? Okay, so we'd go, and I'm going to do my best here to keep it even. If I'm a little off, it doesn't matter. They represent the fractions and the time associated with them. So we go 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 increment, but I need 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. That's it. We've got it. All right? So that's actually not bad. They're pretty even. I like that. Lucky. It's almost like I've done it before. So now all we have to do is place our fraction. Well, this is really easy, isn't it? So our fraction is 14 26. It goes right here. That's where our sample is placed on our number line. Now, right, the bottom is what we're dealing with right now, right? We've got the fractions. We've placed it there. But on the top of the number line, we have it's a number line here. It's a timeline here. Okay, so we've got 710 million years, and we've divvied it up. Divvied means divided, right? We've divvied it up by how much? Well, how many little spaces do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? So we take that 710 million years and divide it by 13, because that's what we did. We've divided that much time by 13, right? So you do the math. So what is 710 million years divided by 13? Calculator. Actually, be more like 54.6. 54.6. So what is that? It's 54.6 million years for each of those increments. Okay? So if we've got 710 million years down here, and we're just backing off, we're backing off 54.6 million years to find the age of our sample, what do? If it was all the way at the end, it'd be 710 million years old, but our sample is one increment in, more recent than that. So you'd subtract. So you'd take that, each increment's 54.6 million years, you'd subtract one of those, since you're only one increment away from that, you'd subtract it from 710, and you find your answer.
655.4.
655.4. I'll go up, since we got the time up here. So what was it again?
655.4.
655.4 million years old. That is, MYO, million years old. That is the age of our sample, okay? You could also say, all right, well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 54.6 million year increments from 0 years old. And you could just take 12 times 54.6 and you'd get the same answer. So you can come at it from either side, but since we're way over here, just one away, you might as well just subtract it from 710. Okay? So I hope that makes sense. This has been probably the simplest, she picked a good fraction, okay? It wasn't too complicated. We didn't have a whole bunch of increments to deal with, but that's how you do it. So like step 1, you have your sample's fraction of parent to parent and daughter isotopes. The second thing you do is you determine where does that fraction fall on the chart, and then you take what it falls in between, those two that it falls in between, and you open it up into a timeline like we did here, timeline and number line fractions, right? Then you get a least common denominator, which we did with the 26, and then we put our increments, and we divide by the number of increments, right? And then you finish the math off like we did. So pretty good. I have a question from the audience here, the class. What is it?
If you multiply it, wouldn't be the same answer.
It wouldn't.
Maybe
Do it.
it's 0.2 off.
Oh, because it rounded. You rounded probably. What's the answer? If you take 54.6 times 12, what do you get?
655.2.
Okay, so we're off by 0.2, and that was probably due to rounding. Okay. That's your question? Awesome. She's like, sure. Yeah. So if you have any questions, bring those up in the Zoom class. If you see this before Wednesday, I don't think you will. So you probably be able to actually ask me about this stuff if you have questions in class. Imagine that. I can't wait. Thanks for watching.